Okay, the midterm questions and solutions are on OTTI class. If you haven't seen them, you should also have received your graded midterms. And just have a look at the solutions, check your grades. If there's anything wrong, let me know so that I will be able to correct it. And look through the solutions. If there's any solution that's not clear, we can discuss it tomorrow in detail. Okay, any questions before we start? The homeworks were due tomorrow, right? Tomorrow or, no, it was due Friday. The homeworks are due Friday. You will get a new homework today or tomorrow for next Tuesday. So since you are already having midterms also yesterday and today, I think, so we postponed it to Friday. Other questions? From what I see from your midterms, you should be having lots of questions. Yes.
Hocam şu eksi Q ile artı 2Q mesela diyelim. Böyle iki farklı yük var. Bunların arasındaki polarity nasıl olacak?
Which polarity? Dipole moment. Well, the definition of the dipole moment, you see, we had this general definition of the dipole moment. If you have more than one charges, it is just this one, independent of how many charges you have. So if you know their positions, if you know the charges, just calculate that sum. That is the dipole moment. So if you have many charges, well, just for each one, multiply the charge with its position and sum them up. You don't have to have a plus Q and a minus Q. Whatever the charge distribution is, this is always the definition of its dipole moment. So looking at this definition, even a single point charge can have a dipole moment. Now in the exam, you had this problem of two charges, plus Q, minus Q. Well, there will be these two image charges here. Here you will get, let's say, Q prime, here minus Q prime. So these will be your two image charges, and the dipole moment will be just this sum for these four charges. Because you see, the dipole moment determines what is the potential for a faraway observer. And for a faraway observer, the potential created by this single conducting sphere and two charges is the same as the system of these four charges, two real, two image charges. So the dipole moments should also be identical. Well, in this question, you mean Q and 2Q. This system does have a dipole moment. You see, let's just choose the origin over here. Or let's choose the origin here. This is our origin. This is the x direction, this is the y direction. Let's say this distance is d. In this case, the dipole moment of this system will be Q times the zero vector plus 2Q times d in the x hat. This is the dipole moment. And hence, the dipole moment vector is 2q dx hat. The system has a dipole. Okay, that is the information in your first year's lectures because it's the easiest dipole system we have. But for any charge distribution, whatever the total charge is, you can always define a dipole. Of course, if the system is not neutral, if it is charged, the potential at large distances will mainly be determined by the total charge. And the dipole will just give a very small correction to the potential, but still you have a dipole moment. Other questions? Well, the boundary condition is that it should be periodic. You don't need the zero condition there. Look at the solutions. If the solution is not clear, we can discuss tomorrow in more detail. Questions?
Hocam, bu Poisson equation'ı kullanarak surface charge density bulabilir miyim?
Well, if you do it properly, yes. Of course, the Poisson equation, you see, if you know the potential, just act on the potential with the Laplacian, you will get the volume charge density. A surface charge density will be, you can write the surface charge density as a volume charge density with a suitable Dirac delta function. That is what you will get. You see, when we are discussing about the surface charge densities, we are always saying that it is we can calculate it using the discontinuity of the electric field. Laplacian of the potential is nothing but the derivative of the electric field. If the electric field is discontinuous, like the step function, then its derivative gives us a Dirac delta function. So if you pay attention to that, then you can obtain the surface charge density also using the Laplacian or the Poisson's equation. But it will be easier to look at the discontinuity in the electric field. Yes, other people.
Laplace'dan bahsettiniz mi hocam? Ben gelmeden Laplace'dan bahsettiniz mi? Yani verdiğiniz şeyi ben tam olarak anlamadım. Tipler tamam ama kesitte nasıl gözüküyor? Yani potential'lar y'ye göre nasıl fark gösteriyordu?
Well, the solutions are on the auto class, so I didn't really discuss the midterm questions. We can just look at the solutions. If things are still not clear, we can discuss it in more detail tomorrow. But for example, is it clear to you how to use the separation of variables? Then why don't you ask? So is the separation of variables clear to you? Okay, he said no. I can explain to her after the class if everybody else understood it. Okay, everybody understood it, so we can discuss after the class. Yes, other questions? So let's continue with this dipole moment. Now, most of you are more familiar with the dipole moment of neutral systems, the positive charge and the negative charge. Well, where do we get these dipole moments in real life? Well, we have the atoms that are neutral. So you see, we can say the atom crudely is a spherical object with a nucleus at the center. So this is the electrons. Here you have the nuclei, which is positively charged. So this is our atom. And if you put this in an electric field, well, basically the size of the atom is very small, and most of the electric fields that we can create do not really change over the size of the atom. So you can just think that the atom is uniformly charged, more or less. The electric field is uniform over the size of the atom. So what will happen to the electrons? Well, the electron will move in the opposite direction of the electric field, and the nucleon will move in the direction of the electric field. So this was the original system. The nucleon will be slightly shifted relative to the electron. So this was the original position. Now that is the new position. That dot is the center of the electron cloud. And the separation is mainly, let's just say that it is separated by a distance d. Now the question is, how can we calculate this separation d? So once we can obtain this d, the dipole moment is just we have a charge q, which is the charge of the electron or the nuclei, displaced by a distance d. So the magnitude of the dipole moment is basically q times d. So to calculate the dipole moment of the system, we need to somehow estimate the d, this distance. So how can we do that? I mean, why does the nucleon stop there? I mean, so we have this external force acting on the nuclei and the electron, and they're also exerting forces on each other. So when these two forces when the nucleon is at the center of the electronic cloud, typically there won't be any force acting on, the net force acting on the nucleon due to the electron will be zero. But as the nucleus is shifted from the center, there will be a force acting on the nucleus due to the electrons, plus there is this external force, and they will be shifted relative to each other until these two forces balance each other. So to calculate this distance d, basically we need to determine what is the force acting on the nucleus due to the electronic cloud. So that is what we need to kind of estimate to be able to determine d. So how can we calculate this distance d, assuming we don't know anything about quantum mechanics? What will be a simple model? The simplest approximation that you can think of. So first we need to calculate the electric field created by the electron cloud, but to be able to calculate this electric field, we need to know the charge density of the electrons. So what can be just an approximation? Maybe a crude one. Where is the charge density of the electron? Well, they are both shifting. So we have, let's say, this is the nucleus, this is the electronic cloud. So when the electric field applies, the nucleus moves in one direction, the electronic cloud moves in the other direction. So this is our new equilibrium point. In the equilibrium configuration, the distance between the center of the electronic cloud over here and the center of the nucleus is what we call d. They're both shifted. So now we are interested in the force acting on the nucleus due to the electrons. So a simple model for the charge density of the electron. Spherical shell, okay, that's a good enough model. So you are saying that the electrons can be a spherical shell. This is where we have the electrons on the surface. And what is the electric field of created inside a spherical shell? Well, 0, so there won't be any force acting on the nucleus. A good try, but unfortunately doesn't seem to be consistent with our observation. The next simple model, and that would be the simplest choice if it had worked. So the next simplest thing that you can think of, that's not simple. You already saw it in the homework.
Dipole.
Which dipole?
Yani proton elektron.
Now, we are trying to create a kind of a realistic model, not very realistic, but at least that can capture some of the fundamental properties of the electronic charge density. What is the electronic charge density? Okay, so where is the charge? Uniformly distributed over the volume. Well, that is the second best choice, second simplest choice. It might work. Let's give it a try.
Negatifler yapabiliriz aslında. Dışarıda elektronun yani şey olarak dağıldığını düşünüyoruz.
Well, it's not grounded. And he said that it should be uniform. Uniform doesn't work. Well, you are proposing to treat the electronic cloud as a charged sphere on the shell. That will be an alternative model. You mean a sphere at the center and the shell outside?
Yes. Yani elektronlar bir yöne doğru kayıyorlar ya, yarı küre bir shell olacak. Yani hemisfer bir shell olacak. Tamamını kaplamayacak.
Oh, so you are saying that we don't have this model, but we should have a shell over here. But the problem is our model should also reproduce the equilibrium configuration. So in equilibrium, the nuclei should be forced to the center. If you only have a shell, and we will be assuming, making many approximations, that the general charge distribution of the electrons do not change. So of course we can come up with more complicated models where the electrons in the presence of the electric field will be covering part of this shell but not the rest. That's also possible. Or as you said, we can just treat this a shell charge distribution and assume that it's a conductor. It can move on this surface. And then we put this positive charge, and then we can try to see how it behaves. But the problem with that model, at least, is if you just treat this as a conducting shell with a net electric charge, now once the nuclei is shifted in one direction, so the the negative charges will be accumulated in this region, the nuclei will just hit the boundary. It will not be stable at the center. That would be the problem with your model. So one of the simplest things, or if you want to cook up a model in which the electrons is distributed only over the part of the shell, we have to also come up with a method of calculating what fraction is occupied for a given electric field. Because for a zero electric field, it should be more or less uniform.
Hocam şöyle yapıyoruz. Elektrik field'in kuvvetine göre oradaki alan büyüyor ya da küçülüyor.
Okay, that is good in words, but we have to formulate it. So that is where things start to get more complicated. So we have to be able to calculate things rather than just say things. So that's the next step. First, of course, you speculate about the possibilities, but then taking those possibilities, you formulate them. So you would come up with problems formulating that thing. But we already have a formulation for a uniform sphere. So we can assume that the sphere has a total charge density Q over 4 over 3 pi r cubed. This is the volume of my sphere. Now the electric field at a distance d, to calculate the electric field at a distance d from the center, this is d, what you can do is you can just assume such a Gaussian surface, a spherical Gaussian surface with radius d. So the total charge inside this volume will be, well, this is the q over 4 over 3 pi r cubed is the total, not the total, but the charge density. If you calculate it with the volume, pi d cubed, this is the total charge inside our volume. And we know that for a sphere acts like a point charge with total charge at the center. So the electric field created by that much charge is just 1 over 4 pi epsilon 0 times 1 over d squared. This is the magnitude of the electric field. The charges outside the sphere do not create an electric field, basically because we already know that if you have a uniform spherical shell with uniform surface charge, there is no electric field inside. So all these, this is a uniformly charged spherical shell with uniform charge density. That's our model. We are assuming that the charge density is uniform, so inside there won't be any electric field created from these charges. Only these charges will be creating the electric field. And this will be the magnitude of the electric field. And this should be equal to the external electric field, so that the two will cancel and the relative separation between the electrons and the nuclei will be stabilized. They won't be moving anymore. So if you just make the simplifications, this 4 pi over 3's cancel, this d squared cancel this d over here. So q times d divided by 4 pi epsilon 0 r cubed will be should be equal to the externally applied electric field. Or the dipole moment of this very simple system, the magnitude of the dipole moment will be 4 pi epsilon 0 r cubed times E. Or let's say, even vectorially, this will be true. The induced dipole moment of the system will be in the direction of the electric field. Of course, you can come up with more realistic models, but mainly the dipole moment of the system will, in most of them, will have this form. There is this volume dependence. It depends linearly on the volume. 3 epsilon 0 times the volume, and it's in the direction of the electric field. Now, of course, for a more realistic model, maybe you won't get 3, you might get 5 or 8, but basically it doesn't, just that numerical factor doesn't really change our understanding of what's going on.
Hocam şu kutunun altındakini öylesine yazdık değil mi? Bu formda da olabilir. Yani üsttekini türettik biz.
Now you see, volume is 4 over 3 pi r cubed. So 4 pi r cubed is just 3 times the volume of the atom. In this model, in the simple model, where we are modeling the atom as a spherical object with a uniform electric charge density spread over the volume. Now, in general, if you have, I mean, this is what we call the dipole moment. In the book, it says created by the displacement. So the basic idea is that initially your atom doesn't have a dipole moment. The center of the electrons and the center of the nuclei, they overlap. So D initially is 0. And then you apply some charge. So you apply some electric field on your dipole. And once you apply on your atom, once you apply an electric field, the nuclei and the electrons, they just move in opposite directions. So their centers will be shifted relative to each other. And that creates the dipole moment. And this coefficient, I mean, even if you don't have a simple model, for a simple atom, the polarization will be a function of the electric field. And any function, you can make a Taylor expansion. We have this Taylor theorem. So you can expand any function in terms of the components of the electric field. So you will have, let's say, one coefficient times the electric field plus terms that are proportional to the square of the electric field, the cube of the electric field, etc. This coefficient alpha is what we call the susceptibility. So it is how susceptible your system is to polarization due to an electric field. Susceptible, eğilimli, etkilenebilir. So that is basically how much the electric field can influence, can modify your system. Now, if you have a single atom, then the polarization will almost always be in the direction of the electric field. But when you have molecules, things start to get a bit more complicated. For example, if you look at the carbon dioxide, which you have a carbon atom over here, oxygen atom over here, another oxygen atom over there. If you exert an electric field in this direction, well, the electrons can easily move along this molecule. So the electrons will move a large distance. But on the other hand, if you take your carbon dioxide and apply an electric field in a direction perpendicular to the alignment of the molecule, well, the electrons cannot really move that much. So in this case, the susceptibility will not be just a number. I mean, if you take the carbon dioxide, now in this case, if you apply an electric field parallel, of course, the dipole moment will be in the direction of the electric field. If you apply an electric field perpendicular to the line of your molecule, the dipole moment will again be in the direction of your electric field. But if you apply an electric field in this direction, so you see the electric field will have two components. There will be the component parallel along the line of your molecule plus a component perpendicular to the line of the molecule. And this component parallel to the line of the molecule will create some dipole moment. And the component perpendicular will also create the dipole moment. And this will be the total dipole moment created by this charge distribution. But this time it is definitely not equal to some alpha times E. Because these two numbers need not be equal. It will be easy to polarize the molecule along its line than perpendicular to its line. So in this case, we say that P, let's say if we write the components of this dipole moment, Px will be alpha x from alpha xx times Ex. It will receive some contribution in the y from the y component, from the z component, and similarly for Py. And here, alpha, let's say Ij, is what we call the susceptibility tensor.
Hocam burada dipole moment'ı displacement ne yaratıyor? Ben orayı anlamadım.
Well, you see, here we had an example. In this example, it was the displacement that created the dipole moment of the system.
Zaten bir dipole momentumuz yok.
No, not in this problem. Of course, we also have other molecules that have their dipole moment. Let's see, for example, if you look at the water molecule, we have the oxygen, hydrogen, hydrogen. Now, the oxygen is slightly negatively charged. The hydrogens are slightly positively charged. So this has a net dipole moment. So you don't need an electric field to create a dipole moment in this case. But let's see what happens if we put this one in an electric field. So let's just assume a simple dipole. We have this plus Q charge over here, the minus Q charge over here. Let's say they are at positions R plus and R minus. Let's calculate. So let's say that we have well, they are connected. They will be just two different ends of a molecule, for example, a simple model. Let's assume that this is in an electric field. Let's first assume it's a uniform one, uniform electric field. What will happen if there's a dipole is in a uniform electric field? Well, this will feel a force in which direction? It will create a torque. So this is F minus. This is the direction of the force felt by the positive charge. And the magnitudes, if E is uniform, they will have the same magnitudes, but opposite directions. So the total force will be equal to 0. There won't be any net force acting on our system. But nevertheless, there will be a torque acting on the system because these two forces are acting on different points. So let's calculate the torque. This R plus cross F plus is the torque contribution to the torque due to the force acting on the positive charge plus R minus cross F minus. This is the torque due to the force acting on the negative charge. But we know that F plus and F minus, they are just opposites of each other. So this is equal to R plus minus R minus cross Q times E. Now R plus minus R minus is nothing but this vector over here, D. This is equal to Q times D cross E. But you see, Q times D is nothing but the dipole moment of this system. So the torque acting on this system is nothing but the dipole moment vector product with the electric field. Although we derive this result for a simple system of just 2-point charges, this is true for any system that has a dipole moment. If you have a system that has a dipole moment, it will feel a torque, and the torque will be given by the vector product of the dipole moment and the electric field for every system.
Hocam burada giderek sönümlenen bir tork var değil mi? Hani iki kuvvet birbirine zıttına geldiğinde sıfırdan geçiyor.
Well, you see, when you are talking about damping, you are basically talking about the time evolution. So, here we are looking only in statics. There is no time evolution here. Now, of course, if you have such a system, unless there are other forces acting on it, so this dipole will try to rotate in this direction. So it started like this. So due to the electric field, the positive charge will feel a force in that direction, the negative charge in this direction. So this system will rotate clockwise. And if there is no friction, etc., the system will start to rotate. It will align with the electric field. When it aligns with the electric field, the torque will be 0. But nevertheless, it has an angular momentum, so it will keep rotating. So it will have such an orientation. Now the torque will try to rotate it in the other direction. So it will just oscillate back and forth. It will make an oscillating system. Now this will also happen for any polar molecule like the water. So if you take water, if you put it in a medium, in an electric field, and then the dipole moment of the water will also try to align with the electric field. But then, of course, there are a couple of issues. If you just consider a single water molecule in vacuum, you put it in a uniform electric field, there's no gravity, so it's not falling anywhere. So it will just make this oscillatory motion. And that's it. Of course, once you learn quantum mechanics, you will see that it will radiate. It will lose energy by radiation, also in classical mechanics, not in only quantum mechanics. It will radiate energy. Eventually, it will stop. But for a long time, it will just vibrate. Well, you don't have water molecules isolated in vacuum. I mean, most of the time you have water, in our everyday life, you have water in the bottles. Or other molecules that have a permanent dipole moment in solids or liquids and even in gases, where the atoms are constantly moving around, they are colliding with each other. And once they collide, the electric field, on one hand, it will try to align the dipole moment with itself. So if you apply an electric field in this direction, the molecules will try to align with it. But on the other hand, all these molecules are constantly moving around, colliding with the neighboring atoms. And these collisions, they don't try to preserve the orientation of the dipole moment. So after the collision, they will just be oriented randomly. So you have these two effects. On one hand, there is the electric field that's trying to align the dipole moments in the same direction. On the other hand, there is this constant vibrations of the molecules and collisions of the molecules which just randomize the direction of this dipole moment. And the final net dipole of your system will mainly be determined by whichever one wins. So in a given electric field, if you increase these oscillations by heating the system, for example, if you increase the temperature, then the total dipole moment of your system, not just the molecule, but of all the molecules, will get smaller. If you lower the temperature in a given electric field, the dipole moment will start to get larger. So now we have these two mechanisms, but whichever the reason is, whenever you have a given material, it can be a liquid, gas, solid, whatever you want, you put it in an electric field, an external electric field, or by an electric field from some origin. So if the molecules are not, they are not already have a dipole moment, so the external electric field will basically shift the charges. And once they are shifted, it will create a dipole moment in the direction of the electric field. So you end up having each atom or molecule will have a dipole moment in the direction of the electric field. The other case, when you have already polar molecules, like the water, they already have a permanent dipole, they will try to align with the external electric field. So without the external electric field, they have dipole moments, but they are all randomly oriented. One points in this direction, the other one points in this direction, etc. So when you sum them up, the total dipole moment of your system will be 0. But if you apply an electric field, it will try to align it in that direction, and you will still end up having a net dipole moment, most probably in the direction of the electric field. Of course, we are ignoring systems which are not isotropic. So here we will be dealing with systems that are isotropic, that are the same in every direction. If you have a system that is formed of layers, it might be easy to polarize it along the layer, but not so easy perpendicular to the layer. But we will be basically ignoring those systems. At the end of the day, you have a material that has a net dipole moment. Most of the time, since we have this continuum system, we will be talking about the polarization, and we will denote it by capital P. This is nothing but the dipole moment density. Or dipole moment per unit volume. What you basically do is you take your system, you take a very small volume, very small compared to the size of your system, but still very large compared to the atomic size. And then the dipole moment is defined as delta P, the total dipole of that volume, divided by the volume. So this is how we define polarization.
Hocam biz şu elektrik field'ı kaldırdığımız zaman bu polarizasyon dağılıyor mu?
Well, it depends on the material. For most materials, almost all materials that you will meet in everyday life, yes. Once you remove this external electric field, all the dipoles, if you are talking about a system consisting of polar molecules, their orientation will be just randomized due to their thermal motion. Or if you are talking about a system that doesn't have a dipole moment without an external electric field, once you remove the electric field, the nuclei will just move to the center of the negative charges, the electrons. So eliminating any dipole moment. But there are systems, very few, which do keep their dipole moment, just like permanent magnets. Now, so if you have any polarized medium, polarized by some means, by external electric field, well, we had already seen that dipoles create an electric field also. So, for example, if you consider this system, put it in an electric field, there is this external electric field, or the electric field created by all the external charges. Plus, now the system is polarized. If the system is polarized, that will also create an electric field, and hence we have two contributions to the net electric field. One, the external electric field, plus the electric field created by these polarized objects.
Şu taraftan çıkan elektrik field ikisini toplamı mı?
Well, you see, this electric field doesn't really enter it. The electric field here will also be modified. So this is just, in the absence of this dielectric, we are saying that let's just assume a uniform electric field. The total electric field will be the sum of the applied electric field plus the electric field due to this polarization of the medium. Now that is what we will study in the next hour. What is this additional electric field? Any questions before you go?
Hocam diploma not olması için yani hem artı hem eksi yükün düzgün olması lazım hem hareketliyken.
You can, I mean, the thing is, for the time being, this semester, we will be only dealing with static systems, systems that do not change in time. That's the limitation we are imposing now. The system can be moving. Next semester, for example, we will be looking at the dynamics, and we will see what happens if the dipole is, let's say, making such a motion. We will see that it radiates electromagnetic radiation, but that is for next semester. This semester, we are only dealing with statics. In a couple of weeks, we will be studying the magnetic fields, and even in that case, we will be looking at currents that do not change in time. We will be dealing with magnetostatics. Now, all these definitions that we are making, they will still be valid when we look at dynamical properties of the charges. But of course, we will need to keep an eye on, because some of the properties will be different. Okay, so I'll see you after 10 minutes.